This is a crash course all about sealants. Things on the outside that go between two materials. They allow flexibility, they stop things from going into them. There's a little bit to know about them, so we'll jump into that. There are lots of different chemistries and materials that sealants could be made from. Our favorite is silicone. Silicones are an inorganic material, which means they are bonded from silicone to silicone. I'm sure it's much more complicated than that in the chemistry, but the effect of that bond is that it's not affected by UV. It's not going to degrade when it's exposed to the outside. That's a really good characteristic of a sealant. Some of the inorganic sealants, like polyurethanes from the 80s and 90s, you may have seen some of those older sealants. They'll start to degrade and kind of turn sticky after about 10-15 years. That is just UV breaking down the organic bonds between some of the links. So the C to O bonds, if you're familiar with inorganic chemistry. In organic chemistry, the silicones are much stronger from that perspective. Silicones are going to have a stretchier characteristic to them. They are stronger in most cases. And bonds to substrates very similar. There are other chemistries like STPEs, sialyl terminated polyethers, also an inorganic chemistry, a bit better than some of the old polyurethanes. So some of that chemistry has come around in the last few years, and we're starting to get better performance out of those newer versions of organics. In the range of, just in one of those categories, let's say silicones, there's actually a whole range of silicone sealants. You may get low modulus, medium modulus, high modulus. That's how kind of stretchy or resistance it is to moving. You get different curing agents, different ways they cure, moisture cured or cured through some sort of chemical reaction. And so just choosing the type of sealant, that can be a chore in itself. The joint profile can have another big impact on the performance of these joints, these sealant joints. When you are looking at the width of a joint, if you have a very, very small joint, it means you have a very small piece of sealant that can go across it. So when you get movement, which is, say, 100% larger, that could be a very small amount. Most sealants can go somewhere between 50 to maybe 150 at some of the higher end of the range. 100% movement is pretty typical range. So if you have a very small joint, then you're gonna have a very small movement capability. If you have a very large joint, you sort of have the opposite problem, in that you actually getting it into the joint in a proper uniform kind of way can be difficult. So most of the times we see sealant joints in the range of 20 millimeters to maybe 8, maybe 6 millimeters at the smaller end, and any range in between that, of course. I have seen larger joints done like that, but it's very finicky to kind of tool sealant correctly to get it to do that. Joint between materials is going to be basically an open gap. So to control how much sealant goes into that sealant joint, you're going to put some sort of backer rod or some sort of framework that the sealant kind of bond, or not bond to, but be supported by. You'd commonly call it a backer rod. Now that backer rod, its main function is just to control the depth of sealant. So you're going to set it into your joint at the specific depth that you want, and it's going to basically be compressed in there and basically hold the formwork to make sure your sealant sets at a certain thickness. The common ratio of width to depth on a sealant joint is 2 times the width, 1 times the depth. So if you've got a 20 millimeter wide joint, you want 10 millimeters of sealant down the middle and a little bit of an hourglass on the outside. You can also do what's called a fillet joint. That is where 2 materials come together like that, and maybe you want to seal that joint between them. Now, if those are gonna move a little bit, if you just installed sealant and didn't have a backer tape or a bond breaker tape in that corner, you'd be back to that very small amount of movement capabilities. So commonly what you do is just run a small strip of tape along that joint first. That can be masking tape. It's not particularly important what it is. Its only function is to make sure the sealant doesn't bond to the substrates. And then that gets you back to performing very similar to a regular joint that you see between 2 materials. So fillet joint, like that. Your common kind of bond breaker or backer rod joint for the wider ones. When you are installing sealant on site, there's a lot of QA processes you can go through to make sure that sealant joint is going to last as long as you want it to, or hope it will. The first thing would be an adhesion test. So when you install sealant and it's cured, you go back and across the joint, you cut one side of the sealant joint, peel it back, and make sure it's bonded to substrate 1, do the reverse, cut to the other side, make sure it's really well bonded to surface 2. Now, what does really well bonded mean? When we're checking the bond strength, we have 2 failure modes. We could either have cohesion or adhesion. Adhesion is the sealant actually sticking to the substrate, and cohesion is failure internally within the sealant joint, the sealant itself. When we're pulling on that sealant, we want to see the adhesion not be the failure mode. We want to see cohesion, the sealant itself actually breaks, which means the bond to the substrate is stronger than the actual joint. That makes sure we've got a really strong and robust joint and bond to the substrate. The next thing we want to check is the sealant profile. Does it have the width to depth ratio we're looking at? Most of the times that's a 2-to-1 ratio. Some sealants will be a 1-to-1 ratio. Just check your manufacturer's specifications. But if you cut out that sealant joint and inspect it from the side, measure the width, measure the sides, make sure it's got the right depth ratio. The next thing that can cause people problems or something to look for on site is air bubbles inside the sealant joint. When you're installing that joint, it's usually coming out pretty consistently. But when you get to the end of the tube, you might start squishing out air, or as you're tooling it, you might introduce some air into the air pockets into that. Probably not going to necessarily cause an immediate problem, but what can happen is those air blisters, when they heat up, they'll expand and they can actually blister. So as you're cutting through the sealant joints, or as you're inspecting the sealant joints, something to look for is air pockets, air blisters, and make sure that none of that's happening. Well, also when you're inspecting the tooling, the shape of profile, you want to make sure that you've applied enough pressure across the sealant joint that you get sealant down into the sides of the backer. It should be a nice hourglass shape. So a little bit concave on the outside and a little bit concave around the backer on the inside. You're looking for basically the bond length. How long is that sealant joint bond across the substrate? Sealant chemistries have made really big inroads and really big leaps in the last 20, 30 years, since the 1980s and 90s, and we started seeing silicones come on the market in sort of the 70s and 80s. And those silicones that were installed back in the 80s and 90s, they're still working just fine. Silicone is commonly used for high-rise glass as a structural sealant, and we don't see any decay. We don't see windows falling out because of failures of those sealants. So when we apply those to the outsides of buildings, we've definitely got the strength, the durability, the UV resistance. These are not the same urethanes that you may have seen fail in the 90s, 2000s. We're also not necessarily relying on sealant as our only means of defense in a lot of these building systems. Even if silicone or sealant did fail, we normally have a backup behind that. Any of the sealant joints that you can see on the outsides of claddings are normally not the only thing preventing water from getting through. We've moved on to that technology of face sealing, and we're now into a regime of rain screen claddings where you've got 2 lines of defense. So sealants can be a really excellent way to finish gaps between 2 dissimilar materials. You don't have to always use cover flashings or some sort of very intricate origami of metal pieces to make that joint happen. Sealants are a wonderful way to make that joint occur.